Okay, so we've seen about a couple of applications of tail bounds in this course, in this module, and now we're going to see something that is actually quite famous. We're going to talk about routing in sparse networks. So here's the plan for this segment. First of all, we're going to define a low degree network. So if you think about networks in data centers and things like that, you need low degree sparse networks because in order to maintain the computers in a data center so that they can I mean you still want it to be low diameter, you want the latencies to be small, but at the same time you don't want very high degree or very high number of edges, dense graphs, because then you will have to invest on a lot of wire. So, a hypercube is one such example that is low degree and low diameter. Okay. So, we are going to define a hypercube, and then we are going to take an illustrative problem, the permutation routing problem. We will define that, and we will point out that deterministic algorithms are bad for solving this permutation routing. We will not prove this, but we will just point that out, and then in this module, in this segment, we will discuss a very simple and very neat algorithm, and it is a little bit counterintuitive possibly, but very nice and elegant algorithm, and in the next segment we will analyze its properties. Okay. Just to motivate, this problem is set in the context of congested networks. We are all used to traffic congestion, slow internet and stuff like that, and sometimes when you see how the flyovers are built in Chennai, you wonder what thought went into that. So, yeah, so this let us actually look at some science behind this. There is something called the Brgess Paradox. So, let me just briefly talk about this. So, this paradox kind of tells you about smart ideas that you might have, but may not, and smart in quotes, that may not really lead to improvements. Let's see what happens over here. So, you have this two cities S and T, and you have two ways to go from S to T, and let us say there are some 20,000 cars that want to go from S to T. Okay. And these routes have two segments each. For now, ignore the dotted road. These if you look at the top route, there is a segment that has this L over 200. This means the time it takes for a car to go from S to A is given by the load, the number of cars that are going to use that route, divided by 200. Okay. So, this is, you can think of it as a small road where if more number of cars go, then there is more congestion, and therefore, there is more delay. Okay. But then the other segment from A to T, if you notice, has a fixed time. So, this is like a highway, plenty of lanes. So, your latency does not depend on the number of cars. Okay. You have a similar situation in the bottom route, except the constant time segment is first, followed by the segment that in which the delay depends on the load. Okay. And so, now our example, we have 20,000 cars, and it is not hard to see that without the middle road that connects A and B. Okay. Ignore that for the moment. You expect people to, it is a little game theory here, people will realize that they if one side gets too crowded, then they will start using the other side, and so the cars will split roughly into 10,000 each. Okay. And it is not hard to see that the latency here is going to be 160 minutes or whatever units of time we want to take. Okay. Why? Because there is 10,000 cars each. So, if you divide that by 200, you are going to get something like 50 plus 110 units for this segment. So, you have a total of 160 units. But let us say let's see what happens if you build this very high speed corridor that connects A and B. Okay. This is very fast and really high investment road that is built between A and B. It takes 0 time to go from A to B, relatively speaking. Okay. But then let us see what happens. You'll start to realize that people will start going from S. So what will be the natural way people will try to game the system? They will go from S to A, then try to use this very fast connection, and then from A to B, and then go from B to T. And what will happen is this will have a snowballing effect, and ultimately everybody will want to do that. And if everybody does that, then we are in a bad situation, because this segment will take 20,000 divided by 200. So, that will take about 100 units, this 0, and this will take another 100 units. So, it becomes the Nash equilibrium, if you will, becomes this bad situation. Okay. So, this is just to illustrate that congestion is important and funny things can happen. So, we have to be very careful, and just being so called smart is not necessarily the right thing to do. Okay. So, this brings us to a contribution by a recent Turing Award winner, Leslie Valiant, known for many things, but we are going to be particularly focusing on the theory of parallel and distributed computing. In particular, one of his famous contributions here is what we are going to talk about today. Okay. So, first, to set it up, we have an n-dimensional hypercube. What is that? Well, basically each node in this hypercube is denoted by an n-bit ID. Okay. And here the number of bits is small n, and so the total number of nodes in this n-dimensional hypercube is uppercase n. Okay. And if you when are two nodes connected or not connected? They are connected if and only if their IDs differ by exactly 1 bit. Okay. So, if you have 1 0 1 1 0 1 1, it will be connected to 1 2 3 4 5 6 7 other nodes. So, for example, it will be connected to 0 0 1 1 0 1 1. Why? Because they differ in the first bit, and it will also be connected to 1 1 1 1 0 1 1, because they differ in the second bit, and so on. Okay. So, now let us actually look at how that hypercube looks, and it's this is an example of a 4-dimensional hypercube. So, notice that each node in this hypercube is denoted by a 4-bit string. That is its ID. Okay. And let us see, this is this node, right. So, who are its neighbors? So, it is connected to this node, and if you notice, they differ in the first bit, and so that is why they are connected. And let us take, for example, this node, they differ in 2 bits, so they are not connected, right. So, this is how an n-dimensional hypercube looks like. Okay. So, it gets a little hard to visualize as the dimensionality increases, but for now the only thing intuition that you need is 2 nodes are connected as long as their IDs differ in 1 bit. Okay. So, this is the network topology or structure, and we want to also understand some of the rules by which this network plays. So, it is a synchronous network, which means everybody has a global clock. It is like a conductor saying this is time step 1, and everybody does something. Then the conductor says time step 2, and somebody then the next step occurs, and so on. So, everybody follows the same clock. Okay. And if you look at any edge in the network, at most 1 packet of information can go through that network per time step. Okay. This is where congestion issues start to show up. Okay. This is the restriction, but it is a realistic restriction, and so if this restriction was not there, this problem would not be any interesting whatever we are going to study. Okay. And so now you may ask, okay, if only 1 can go and a bunch of packets are waiting over here, how do you handle that? Well, just put them in a first in first out queue. Okay. This first in first out queue, there is one queue for every edge incident at this vertex. So, for every edge there are a bunch of packets waiting to go along that edge. So, those packets will be put in a queue and they will be sent out one by one along that edge. So, for each vertex there will actually be n queues in that vertex. Okay. So, this is the permutation routing problem. This is the problem that we want to solve in this Hypercube network setting. Okay. Each node has a packet, each node I has a packet p sub I. Okay. And what do you want out of this? At the end, p sub I, each p sub I should which is starting at node I must reach another node pi I, and this pi is a permutation. So, basically everyone will start with a packet and everyone will end with their corresponding pi I packet. Okay. All right. Pi is a permutation, and you want to, the goal is to minimize the number of rounds required to get this permutation routing to be completed. Okay. And you can sort of see the issue here. So that there are if each node has a packet, there are capital N number of packets. They are all kind of jostling with each other in order to reach their final destination. And remember, along each edge only one packet can go per time step. So, if there is too much congestion that takes place, you have to wait along the way at several steps, and so the number of rounds totally needed in order for all the packets to reach their corresponding destinations can become uncomfortably large, and that is what you want to try and minimize. So, let us start with the bad news first. The bad news is that we are interested in oblivious algorithms. So, oblivious algorithms means this is a very natural class of algorithms in the distributed setting. If you have a packet that is has to go from S to some t. So, t is basically pi of S, the permutation point at which it has to go. The route that it takes should only depend on S and t. Okay. This makes sense because in a distributed setting you do not know what other packets are doing, you do not know what other packets source and destination pairs are and things like that. Those should not be part of your concern. If you are a packet going from S to T, your path should only depend on S to T, and this is a very natural restriction. So, we are only interested in oblivious algorithms, and let us focus first on deterministic algorithms, and let me state the bad news. So, let us fix any deterministic algorithm. You come up with any algorithm that you can think of, and any network of out degree n. So, the degree is bounded by this lowercase n, okay. And of course, there are a total of uppercase n number of nodes. There always exists a permutation, basically this pi that defines for each starting vertex where the packet should end. There always exists a permutation which will force the algorithm to take at least omega of uppercase square root of uppercase n over lowercase n. So, you can ignore this is for understanding purposes. The lowercase n is a small quantity, it is log of the uppercase n, right. But what matters mostly that you need to focus your attention on is it is dependent on the square root of uppercase n. Okay. So, that can be quite large. Okay. So, we want to try and minimize that. Okay. This is uncomfortably large. So, naturally we want to try to see if there is some randomization we can do. So, here is what my good news will be. So, there exists a randomized algorithm for permutation routing on the n dimensional hypercube. It routes all the packets to their destination in O of n, lowercase n number of rounds. Okay. What used to be square root of uppercase n divided by n is now become just log of that. So, if you want to roughly understand what the difference is, so let us say you have n capital N equal to 1 million. Okay. Square root of n is 1000. Okay. But lowercase n is just the number of bits needed to represent 1 million. So, that should be like I do not know 20, something like that. So, small. So, you see that this is a significant improvement. Okay. Of course, we are ignoring constants here, but constants should not play too much of a role here. Okay. And this is guaranteed with probability 1 minus 1 over uppercase n. So, that is with high probability. So, this is the good news. So, let me give an algorithm. Okay. This is called the bit fixing algorithm. Okay. It is a very natural algorithm to route the packets. So, remember each packet is starting from a node, and so let us look at a particular packet. It is starting at a node that has this address A1 through AN, and its destination is this location denoted by this address B1 through Bn. Okay. So, let us work through an example, a simple example. Let us say 1 0 1 1, and it has to, let us say its destination is 0 1 0 0. Okay. These are two nodes, right, in the network. I should probably be clear that they are nodes. Okay. So, from here there will be 4 neighbors, but what the bit fixing algorithm says is you start from let's count the bits from left to right. So, let us start from the first bit. Are the 2 bits different from where the packet is now and where it finally has to go? Yes. So, then you fix that bit alone change means that you have a neighbor where that bit alone is different, right. So, you go to that neighbor. Okay. So, you go to that node. So, this neighbor of that first node where the first bit alone is different. Second bit again is different between where it currently is and where it finally has to go. So, then you again fix that bit. So, it becomes 0 1 1 1. Okay. The third bit again needs to be so pretty much all of them need to be fixed in this case. So, 0 it goes to 0 1 0 0 1, and then finally you fix the last bit, you get to the destination. Okay. So, that in this manner you go from one node to its neighbor by just fixing bits from left to right. Okay. Why is this not good enough? What sort of an algorithm is this? Deterministic. It is a deterministic algorithm. Or what do we know about deterministic algorithm? So, it is always going to take square root of uppercase n divided by n number of rounds. So, it is a very nice looking algorithm, very simple clean algorithm, but it is not good enough. Why? Because it is deterministic, and as soon as it becomes a deterministic algorithm, you have this bad news scenario. Okay. This of course, just to keep in mind, this is done by every packet, because every packet has a starting location and a destination location. So, how do we salvage the situation? Again, now we have to insert some randomization into this, right. So, how did Valiant achieve this? It is a very nice algorithm. It just basically takes advantage of bit fixing, but sets it up in a randomized fashion, but sets it up in 2 phases, and this is the beauty of this algorithm. So, recall that each packet P must be routed from its source to its destination dp, sp to dp. Here is what you do. So, that in the first phase, what does P do, this packet P? It is routed from its source to a random destination, a completely randomly chosen destination using bit fixing, because now source is well defined, it is already where the packet is starting from. You just pick a random n bit string that tells you the random destination that this packet has to go to. And do you know how to go there? Yes, you know how to bit fix your way to that location. And then in phase 2, from that random location, you make your way to the final destination. So, it is a very simple algorithm. It is just 2 phases of the bit fixing. So, each packet just starts from its current location and goes to a random location. From that random location, it goes to the final destination, and both of them work via bit fixing. So, bit fixing itself did not work, but we have salvaged it. Okay. It is a permutation routing, right. So, SP, so basically dp is pi of sp. each face is not a permutation routing. You are absolutely right. So, there can be collisions on the receiving end. So, multiple nodes could choose the same RP. Yeah, that is a possibility. That is completely okay. So, that depends on the local memory of the of each node, and that there is usually some, because you anyway have to maintain the queues and everything in that local machine, right, in that machine. So, that is not the problem. The problem is in the when you go through the links, you can only send one by one. So, this really is the algorithm. So, any questions on the algorithm? Okay. So, hopefully everything is clear. It's basically let us just focus on the analysis in the next segment. In this segment, we have just basically seen a very simple algorithm, and at least the first time I saw it, it was counterintuitive to me. In some sense, it is intuitive, in some sense, it is counterintuitive. So, it depends, there is a subtlety here. Yeah, there is a subtlety here. If you define the algorithm so that phase 1 has to complete before phase 2 starts, then they would have, even if one reached before the other, it both will wait in the destination until it is time for phase 2 to start, and then the phase 2 will start. But then you can actually, the other version where you do not wait is also perfectly legal. It is cleaner. But even if there are collisions, it is not a problem. There will be collisions, there will surely be collisions, they will spread out, but we will actually be studying how to analyze the exact issue that you are talking about. There will be lots of nodes, a good fraction of the nodes will not receive any token at all, any packet at all, which means that a good fraction of them will have collisions, and in fact you can also analyze how many packets will end up in, I mean the maximum number of packets that will end up in some node, and that will turn out it's actually something like n, in this case lowercase n over log n, roughly speaking, and we will analyze these things in forthcoming lectures. Okay. So, this is basically what you are alluding to is balls and bins analysis. So, of course, we have to ask ourselves, how do we establish that this is a good algorithm? It is a very clean algorithm, neat algorithm, but that is what we are going to see in the next segment.